Salve, o discipuli. Today is an exciting day because we get to move on from differential calculus of several variables to integral calculus of several variables. And we will begin by talking about double integrals. So, what is a double integral? I will tell you shortly, but first I want to go back and review a few basic ideas from the single variable case. Given a nice function f on an interval a, b, you'll recall that we can define the integral of f over that interval. And the intuitive idea behind such a thing is that this is a special kind of sum. In fact, when Leibniz introduced this integral symbol, it was supposed to be a stretched out s to represent the word sum, or really the Latin word summa. And it's a very special kind of sum. It's an infinite sum of infinitesimals. We might say it is a weighted sum of infinitesimals, where the dx's are our little infinitesimals, and the f of x is the little weight that we attach to each infinitesimal. The idea is that we take the interval over which we are integrating and chop it up into infinitely many infinitesimally small pieces, like this. Well, not really like that. This is about 30 pieces. As you are used to by now in calculus, we have to think infinitesimally even as we are staring at very crude drawings that obviously cannot be infinitesimal. Anyway, the idea is that each one of these little subintervals, of which there are supposed to be infinitely many, are infinitesimally small. This one, for example, that I've put in blue, and let's just say it is at some typical point x, we would describe its infinitesimal length as dx, which is supposed to signify a little bit of x, an infinitesimal bit of x. And this one infinitesimal at x is supposed to be representative of the infinitely many that are packed into this interval. Now, the idea behind an integral is that we're going to add up all of those little infinitesimals. But we're not just going to add them up. If we just added them up, well, we would just get the length of the interval. Each little infinitesimal is going to be weighted with the value of the function f at that point. I'm going to take my little infinitesimal dx and attach a weight to it, namely the value f of x. And this sort of thing is a typical term in my infinite sum that is going to be my integral. And the idea is that I form products like this for every one of the infinitesimals here, all infinitely many of them, and then with the integral sign, that just tells me sum them all up. And then I have to put the boundaries of integration on there. I'm going to start summing at a, and I'm going to stop summing at b. So as I move from a to b, at every point, I take my dx, I multiply by whatever that height is, whatever the value of f is, and throw it into the sum. When I'm over here, I'll have my dx. The weight I attach to it will be negative, because f of x is negative at that point. Anyway, that goes into the sum. Sum them all up with that integral, and that is all that that thing means. No doubt you have also seen a more formal definition of this as a limit of Riemann sums, which is just a more careful way of capturing this intuitive idea without appealing explicitly to infinitesimals. The idea there is you chop this up into n pieces, not infinitely many, but just n, some large number n. So then the individual bits are small but finite. You form the exact same sum, and then you take a limit of that sum as the size of your intervals goes to 0. We're not going to need the formal definition, but we very much need the intuitive notion of an integral if we want to move on to generalize the integral to functions of 2 and more variables. But before we go there, I want to say one last thing in this simple case that could help us out when we get to more complicated cases. One theme we have seen in this class is that your intuition for functions of one variable usually take you pretty far in understanding functions of several variables. But it's easy to get confused by the fact that functions of one variable always have this nice graph you can look at. And while that holds to a certain extent for functions of 2 variables, it doesn't hold at all for functions of 3 variables or functions of 17 variables. So there's some danger in getting too hung up on a geometric picture in the one variable case, because while you might be able to carry that over to the case of functions of 2 variables, you're not going to be able to carry it over to functions of 3 and more variables. So I just want to emphasize once again that when we see an integral like this, the picture you should think of is not so much a collection of rectangles. Don't think so much about areas. I just want you to think about it as a weighted sum. You are breaking that interval AB up into infinitely many infinitesimal pieces, taking each infinitesimal, weighting it with the value of the function there, and then adding them all up. You don't need the picture of the graph to think about it that way. In fact, if I just get rid of the picture of the graph, leaving only the domain of the function f, my intuitive notion of this as a weighted sum still holds perfectly well. I know I've got my function out there somewhere, and as I cover this entire interval from a to b with all these little infinitesimal pieces, well, what we were doing before makes perfect sense. Take each little infinitesimal subinterval, dx, weight it with the value of f right there. No, I don't have a picture of it, but who cares? I know f has some value there, so I have f of x dx, and then sum them all up, and that gives me my integral. So I think that simple adjustment will actually help pave the way to understanding double integrals, triple integrals, quadruple integrals, or what have you. All right, with that out of the way, I think it's time that we can now actually move on to the case of functions of two variables. We have this notion in our mind of what an ordinary integral of a function of one variable represents. And in keeping with what I just talked about a moment ago, I'm showing you only the domain of the function, not the graph of the function. So now let's say we have a function of two variables. We want to discuss what it means to integrate this function over a particular region of the function's domain. Now again, going back to our one-dimensional case, our domain of f might be as much as the entire real axis, and we talked about integrating over a particular interval from a to b. And what do? We chopped it up. You know the drill. Well, we're going to do the same thing down here. The domain of such a function lives in R2. Yes, we could draw the graph of the function, at least theoretically in this case, but I don't want to. I want to just stick with the domain. And just as in the baby case, we wanted to integrate over a particular part of the domain, particular interval, here in this case, we are going to integrate f over a particular part of the domain, over some chunk of R2. So let's say that the region we want to integrate over looks like this. I'll label it R for region, our region of integration. Now, without writing any symbols down whatsoever, I'll bet you already can see roughly what we are going to be doing here. We're going to chop this up into infinitely many, infinitesimally small regions, take each little infinitesimal bit, attach a weight to it, namely the value of the function there, and add all of those things up. That's the intuitive idea in a nutshell. Let me draw some more pictures and write down some symbols, and we'll flesh it out a bit. Here we go. So I have chopped up this region with this mesh. Now the idea is that this is supposed to be a partition into infinitely many, infinitesimally small little bits like this. As usual, you have to use your imagination. Now, as in the simple case, we said, well, what's going on at a typical point? And we looked at some typical point x, and we had that infinitesimal dx right there. Well, I'm going to take a typical point in my region. This point right here, which we will say is xy, representing just a typical point in the region. And we want to consider the little infinitesimal neighborhood of that point, which I'll put in blue again in keeping with our theme up here. Though up here, this is a one-dimensional region, so these were little infinitesimal lengths. This is a little infinitesimal area, so I don't want to call it dx. It's not, after all, a little bit of the x-axis. It's a little bit of area. So I want to call this thing dA to represent a little infinitesimal bit of area. Now I want to add up not just all the little bits of area, because if I just add up all the dAs, of course, that'll just give me the area of region R. I want a weighted sum of all of those little bits of area. And the weights for those infinitesimals will be the values of the function f evaluated at their locations. So for each dA, I'm going to get a term in my sum. I'm going to take my dA and attach a weight to it, namely the value of f at that point, so that all the terms in my sum will have this form, f of xy dA. And then, of course, the last thing I'm going to do is add all of these terms up. And to signify that this is something that's happening in R2, instead of writing it like this, I'm going to write two integral signs side by side like that, indicating that this is a so-called double integral. Last piece, of course, is indicating the region I'm working with. Now, in the one-dimensional case, that was easy. I could just put the endpoints of the region. To indicate that we're doing our double integral over this region R, all we do is down here below that double integral, we write R. And that's that. Now when you see a symbol like this, you have a sense, I hope, of what it means. A double integral really is just the same idea as what goes on in a single integral. We take a certain region of the domain. In the one variable case, it was an interval. In the two variable case, it's some region. Chop it up into lots of little infinitesimal bits, weight each one with the value of the function there, and then add them up. That is what integration is all about. And frankly, at this point, you should be able to understand what is meant by a triple integral or a quadruple integral or a quintuple integral or anything beyond that. Let's consider a triple integral, for example. If I have some function of 3 variables, well, now I can't draw its graph even if I wanted to, but I can still think about the domain, which would live somewhere in R3. And I could take some region of that domain, maybe some blob like this, and let me call that region R. Now, if you are confronted with a terrifying-looking triple integral like this, you should already at least have a sense of what this thing means. We're looking at this region R right here. Okay, well, that's just some chunk of R3. And we're doing an integral, which is always a matter of chopping up into infinitely many infinitesimal pieces, weighting those infinitesimals with the value of a particular function, and then adding them up. It would be hard for me to draw the little mesh that I drew over here, so I'm not going to try, but you can imagine chop, chop, chop in all 3 dimensions like this until you have cut it into little infinitesimal pieces. And let's just draw a typical one in there, a little infinitesimal box. And let's say the center of that box is at X, Y, Z. To continue with my color scheme, I'll put that thing in blue, and we would say that the volume of that little infinitesimal box is dV, a little infinitesimal bit of volume. Well, we take that volume, we attach a weight to it, namely the value of that function right there, put it there, and then add everything up. We have a different term for every one of the infinitely many little spots throughout that region. And the result of that sum is our triple integral. Not so scary after all. For that matter, if I had a function from R4 to R, now I can't even draw you the domain, but nonetheless, we know the domain is some subset of R4, and if we could find a way to specify some region of R4, then we could do a quadruple integral of f over that region. It might be hard to visualize, but conceptually the idea is not hard. We chop that 4-dimensional region up into infinitely many, infinitesimally small bits, weight each bit with the value of f at that bit, and then add them all up. That's it. Same story if instead of a function from R4 to R, this were a function from R42 to R. You might not be able to visualize it so well, but conceptually you understand what's going on. Okay, if you have that much, you've come a long way. But let's get back to functions of 2 variables. Functions of 2 variables are special because we can draw graphs of such functions, or at least we can see graphs of such functions. Drawing them is often a pain unless they're particularly simple. And because I can see graphs of such functions, I can actually interpret double integrals in terms of volumes, in the same way that I could interpret single integrals in terms of areas. We had earlier in this video a picture not just of the domain of this function, but of its range as well, something like this, and you know from your earlier coursework that we could interpret this thing as the area under this curve and over this interval. You also know, I hope, that if this function dips under the horizontal axis, then we would interpret as a difference of 2 areas. Well, anyway, we can do the same thing down here. Because my function of 2 variables, I can graph it, and the graph would be some kind of surface in R3. Now, my region that I'm integrating over, of course, lives in R2, something like that. Now, if we recall what goes into the integral, we take each little infinitesimal piece, dA, like this bit right here, and then we attach a weight to it, the value of the function at that point. Well, the value of the function at that point, of course, is the height of this surface. And if I multiply that little infinitesimal bit by the height of the surface there, I get the volume of this little infinitesimally thin column, right? The volume of that little column would be, of course, the product of its base's area times its height. Well, the area of the base, we've already said, that's dA. So I'll put my dA here. As for the height, well, I'm evaluating this thing at the point xy in R2, so the height is going to be f of xy. So I'll put that right there. So this little bit the thing that we are integrating in our double integral, that represents the volume of that little column, just as surely as f of x dx, we could think of over here the area of that little rectangle right there, because the dx is the width of that rectangle, and the f of x would be the height of that rectangle. Now add up all of those rectangles, and you get the area under the curve. What happens over here? The sum of the volumes of all those columns add up, imagine a column at every one of those points, and we would get the volume under the curve and above this region. Maybe that would end up looking something like this, so that this double integral would end up representing the volume of this strangely shaped chunk of R3. Now, I'm sure you know from your earlier math classes, or maybe physics classes, or chemistry classes, or even economics classes, that the whole idea of using an integral is that you take some function that is varying and is complicated globally because it's constantly changing its value. And by shattering its domain up into little tiny pieces, infinitesimally small pieces, so small that this thing doesn't have time to vary within any one of those pieces, you can analyze what's going on one of those tiny pieces where the function is effectively constant. And then by adding everything up, by reintegrating the whole after you broke it up in that process of disintegration into lots of little infinitesimal pieces, by reintegrating, or just integrating as we say, you can use your information about how the function behaves locally to understand what is happening globally. Typical calculus example would be like this function represents the velocity of a moving object as a function of time. So we're thinking of the independent variable here as representing time. Well, the velocity is varying all over the place. If I want to know how far did the object travel between A and B, if I break it up into little infinitesimal pieces, if I'm just looking at this little infinitesimal bit right there, I can say that the velocity is effectively constant on that little tiny infinitesimal interval. Well, if the velocity is constant, then I know how far it traveled on that interval. However much time elapsed, this would be like a dt, times its speed on that interval would give me the distance traveled in that little infinitesimal interval. And then I add them all up, and that would give me the total distance traveled. The same kind of applications occur in this case. It's just when we have functions of two variables. If we have something that's very complicated globally, we might be able to break it up, disintegrate it into lots of little pieces that will be easy to study, and then we integrate to learn something about the big picture again. A conceptual example from physics might help a little. This is supposed to be a hand. Let's suppose that this hand belongs to some spirit inside of your computer who is, even as we speak, pushing on the screen, trying to break through. Well, whether or not it succeeds will depend on how much force it can exert on the screen. And let's say, through some miracle, we're able to detect how much pressure the hand is exerting on the screen. Well then, you might remember that force, the thing we want, is pressure times area. So I know the pressure. If I could just figure out some way of estimating the area of this hand, then I could see if it can muster enough force to break the screen. But there's a problem. This relationship holds if the pressure is constant. Well, realistically, if you or some ghostly spirit is pushing on something, different parts of your hand are going to push with different pressure. Under here, right where that big muscle is probably going to have a lot of pressure. Some of the spots right under the knuckles, there'll be hardly any pressure. Okay, the pressure the hand is exerting is not constant, but if I could imagine chopping this hand up into infinitely many infinitesimally small bits, like so, at least if you use your imagination a bit, then if these are actual infinitesimal bits, they're small enough that although the pressure does vary all across the full hand, if I focus on one particular bit, like this one, then the pressure is effectively constant there. So if this is an infinitesimal neighborhood of this point xy in R2, I could tell you something about the force exerted just by that one little bit of the hand, because the pressure really is constant there. In fact, the force exerted there would be the pressure at xy, which is constant because we're on an infinitesimal scale here, times the area of that little bit, which is going to be dA, an infinitesimal little bit of area. And now I want to do that not just at that one spot, but all over and add them all up. So to do that, all I have to do is do the double integral, and what goes down here, I am integrating over this hand. So I'll just put my little hand down there. This is, of course, deeply serious mathematical notation. All right, you get the idea though. This holds only under certain circumstances when pressure is constant. The pressure varies quite a bit over the hand, but if we focus just on an infinitesimal bit, it is constant on that tiny little piece. So we can use this formula on a typical tiny piece, in fact on all of the individual tiny pieces, and then just add up the results. And that will be the total force exerted by the hand. Let us pray for the sake of your safety that it is not too great. Okay, we're off to a good start. We know what a double integral is, what it represents conceptually, but the question remains, how do we actually compute one of these things? We know that any specific double integral is a sum and therefore it should be equal to some number. How do we find that number? For the remainder of this video, I'm going to concentrate on a specific case, namely the case where R is a rectangle whose sides are parallel to the axes. Such a rectangle can be described as the set of all points in the plane whose x-coordinates are between some two numbers a and b, and whose y-coordinates are between some two numbers c and d. There are various symbolic ways to describe such a region, but the one I'll use, which your textbook author also uses, is this one. We have the interval AB, which corresponds to the interval on the x-axis, the interval CD, which corresponds to the interval on the y-axis, and this little cross in between them. So nothing fancy, this is just a symbolic way of representing this particular rectangle. Well, I will clear this stuff out of the way and do an example so you can see how it works. All right, let's see if we can compute this particular double integral. Here, the function that we are integrating is this linear function in x and y, 12 minus 2x minus 3y, and we're integrating over a rectangle. Now, while it's possible to graph this function, in fact, it's pretty easy, and I'll do it a little later, for now, I just want to concentrate on the domain. When we are working with multiple integrals, it's usually just the region of integration that we are interested in, and it's important to have a good feel for what that region looks like. Here is our region of integration, the rectangle whose x values run from 0 to 2 and whose y values run from 0 to 1. Now, conceptually, we know what this integral refers to. We imagine breaking this rectangle up into infinitely many, infinitesimally small pieces, and at every little piece, we evaluate the function, namely this linear function right here. We evaluate that function, multiply by dA, the little infinitesimal bit of area, and then add everything up, get the result of our weighted sum, and that will be our integral. We're going to do this essentially one dimension at a time. Suppose we decide to fix some particular value of y. Let's just say it's this blue dot I've just put on there. We're just going to suppose for a minute that we have decided in advance that all we're interested in is this value of y. And we're just going to let x vary so that we will end up with a line coming like that. Now imagine that instead of integrating over the whole region, we just want to integrate over that line. Well, now it's no problem. Now it would be the kind of thing that you could have done in the first class where you learned about integral calculus. Because now we're just asking to go along this line, stop at every little point, every little infinitesimal neighborhood, evaluate the function at that point, multiply by a little bit of length, and move on down the road. It's exactly what you did in your first integral calculus class. And if you did that, what you would end up with would be that at every spot, you'd evaluate the function and get something of this form. I've put the y in blue to remind us that it's fixed, that the only thing that's varying on that line is actually the x, times the length of that little infinitesimal neighborhood around that point, which of course would be dx. And you would have to add up all of those terms as you traveled from here to here. In other words, as x went from 0 to 2. So we'd be adding them all up as x runs from 0 to 2. With y fixed, that integral would give you part of what we wanted. It would give you the sum just restricted to that one line. But of course, there are infinitely many lines like that. And if I asked you to do this at some particular point, like let's say we did this where y is 1/3, well then we would just pop 1/3 in there, and we would have 12 minus 2x minus 1, so it would be 11 minus 2x. And of course, we know how to integrate 11 minus 2x with respect to x, and we could actually come up with a value for what happens when we integrate this function just on that one line. But we don't want just that one line. We want to integrate over the entire region. Still, this is a good start. The thing to recognize is that the value of this, which again is just going to be some particular number for any particular value of y, depends on the value of y we started with. If I had started up here and computed this same thing, then y wouldn't be 1/3. y would be whatever that is, maybe 4/5. We'd have a slightly different function that we'd be integrating with respect to x. This term, of course, would now be 12/5, and when we integrate that different function, we'd get a different number at the end. So integrating this function along the blue line and along the green line give us different values. Anyway, I don't want the sum just on the blue line or just on the green line. I want the sum on every horizontal line. If I could get it on every horizontal line and add all of those up, then I would have the double integral over the entire region. How am I going to do that? I'm going to integrate, because this whole thing, this integral, is itself a function of y. That's what we've been talking about. For different values of y, we would get a different value of that sum. So this whole thing I can think of as a function of y, which means I can integrate it like any function of y. Let me put it in parentheses and remind you that this is a function of y. Since it's a function of y, I can integrate it as y runs from 0 to 1. And this crazy-looking expression will give the exact value of our integral. Let me make a little room for myself and I'll write that down. Okay, now my sentence has a subject. This double integral is going to be equal to all of this stuff. This stuff, by the way, where the function inside my outer integral is itself another integral. When we have a situation like that, we call it an iterated integral. And because this is hard to read with these parentheses on here, we typically do not include those parentheses. So let me just erase those very rapidly, and I'll get rid of this stuff too, and I'll bring that stuff a little closer together as well. That's better. That is how we would normally write an iterated integral, except of course everything would be the same color. And I'll compute this in a moment explicitly, but I just want to emphasize that this equal sign right here, this is the most crucial piece of the whole operation we're doing right now, because what it is doing is relating our double integral, the thing we want to compute, to an iterated integral, which is a thing that we can compute. It may look intimidating for the moment because you've never seen anything like it, but mechanically it's really no different than anything you did when you first met integration in a previous course. All right, now that we have reduced our double integral to an iterated integral, let's actually do it. Remember, whenever you see an iterated integral, there's implicitly a set of parentheses. So as usual, you would expect me to begin with the inner integral, because that's what's inside the parentheses, and work our way out. And that's exactly what I'm going to do. So we're going to forget about everything that is outside the parentheses for just a moment and get back to it later. So we'll just carry along the outside stuff and concentrate on what's going on the inner integral. Now I'm integrating this function with respect to x. The way I'm going to do that is treat y as though it were a constant, because this corresponds to this picture over here, where I'm thinking of some fixed y and only x is varying. So I'm integrating only where x is varying. I'm treating y as a constant. This is a lot like taking partial derivatives, where we treated one variable as a constant. Anyway, if I treat y as a constant here and integrate this function with respect to x, I'm going to get 12x minus x squared. That part is easy enough. What about this third term? I'm treating y as a constant. Well, if I integrate a constant with respect to x, I get that constant times x. So I'm going to get minus 3yx. And of course, thanks to the fundamental theorem of calculus, I can evaluate that at the endpoints as x is running from 0 to 2. So I'll put that here as x runs from 0 to 2. And I'll carry out the calculation in a moment, but don't forget to bring the dy down. That's just sitting on the outside like that outer integral. Okay, now I have to evaluate that, but that's just arithmetic. When I pop 2 into this for x, I'm going to get 24 minus 4 minus 6y. And since 24 minus 4 is 20, I get 20 minus 6y. Now I have to subtract off the value of this thing when x is 0. But of course, when x is 0, I get nothing. So I'm subtracting off nothing, so I'm not even going to bother to write anything there. So I get 20 minus 6y, and my dy, of course, just comes along for the ride. It and its accompanying integral sign have just been waiting in the wings this whole time. Now we can bring them onto the stage to do this last integration, which is easy. Now this is like a problem you would have done long ago. It's just an ordinary integral, and when we do it, we get 20y minus 3y squared, and we're going to evaluate as y runs from 0 to 1, and when we do that, we get 20 minus 3, which is 17. Hallelujah, we have just done our first double integral. Not so bad, is it? As always, be sure you write your work up sensibly. Your argument should begin with the subject of the sentence, the integral you're trying to evaluate. Turn that double integral into an iterated integral, and then the rest is just going to work and reaching, hopefully, your final correct answer. By the way, this crucial equal sign here again, we did it by breaking our region of integration up in this particular way. First, we integrated with respect to x, and then we integrated with respect to y. We didn't have to do it that way. We could have instead started by first integrating with respect to y, then integrating with respect to x. So getting everything in a vertical line and then sweeping it out horizontally to cover the whole rectangle. Let's see how it would be done that way and verify that we will get the same answer, which of course we had better get the same answer because the double integral is just a sum. You had the same sum up in two different ways, you had better get the same thing. So if we're going to start by integrating with respect to y, that means that we're fixing some particular value of x and just letting y vary. Well, if I do that, how is that going to give me an iterated integral? Think about what's happening just on that line with some fixed value of x. I have my function 12 minus 2x minus 3y, where again, for the moment, I'm thinking of x as fixed and only y varying. So I could think of this as a function of y, and I'm going to integrate with respect to y, as y runs from 0 up to 1. Good. Now for any particular value of x, this is going to give me some particular number, but it'll be a different number for different values of x. For this value of x, I'll get some particular value of this integral. If I had frozen x right here, I would get an integral with a slightly different value. So this integral itself is a function of x. It depends on the value of the particular fixed x we have. Since it's a function of x, I can integrate it with respect to x. Now, instead of putting parentheses around it, I'm just going to leave them off. I think by now you get the idea. And I will be integrating that function with respect to x as x runs from 0 to 2. So that inner integral essentially tells me what happens when I add everything up on one vertical line like that, and then the outer integral says let's just sweep that thing across the whole rectangle, giving us all of the terms in this double integral that we need. Good, and the rest is mechanical. We start with the inner integral. Integrating with respect to y gives us 12y minus 2xy minus 3/2 y squared. And we're evaluating as y runs from 0 to 1. When I pop 1 in for y everywhere it appears, we get 12 minus 3/2. Well, 12 is 24/2, so that's 21/2 minus 2x. And don't forget to bring the dx down. That's an easy integral. There's the antiderivative, and when we evaluate, we get 17 as expected. Good. Last thing I will note about this problem is that since this is a particularly simple integrand, and the region is particularly simple, I'm going to go ahead and draw the graph of this so we can see what's going on graphically as well. Okay, here I have the x, y, and z axes, and in the xy plane I have drawn my region of integration. Now the function we are trying to integrate is particularly simple. It's linear, and we know from our earlier work that the graph of a linear function of two variables is a plane. A plane is determined by 3 points, so if I can just plot 3 points here and join them, I will have the graph of my plane. Well, the easiest 3 points to get by far would be the place where the plane intersects the 3 axes. So let's just get those very quickly. Here's the equation of our plane. Where does it cross the x-axis? Well, wherever it crosses the x-axis, the y-coordinate is 0 there. Also, the z-coordinate is 0 there. So popping in y equals 0 and z equals 0, we get 0 equals 12 minus 2x. So x has to be 6, which means that this is going to pass through this point right here at 6. Similarly, where does my plane cross through the y-axis? Well, wherever it crosses the y-axis, x is 0 there and y is 0 there. Putting x and y equals 0 here, I get 0 equals 12 minus 3y. So y has to be 4. So let's just put that here. And finally, where does it cross the z-axis? Well, for every point on the z-axis, x and y are both 0. If I put x and y both 0 here, I get z equals 12. And there it is. So this plane passes through these points, which means that if I'm just looking in that first octant, where x, y, and z are all positive, and that's all I care about for this particular problem, the plane would look something like that. This double integral, what would that represent? That would be the volume of the figure that lies under the plane and above the region. Something like this. Kind of looks like a crystal or something. Rectangular base coming up here, kind of just looks like a rectangular box for a while, but then we get this weird sloping roof. This double integral, we have said, will be the volume of that solid. And that volume, in fact, we have found is 17 cubic units. But can I relate it specifically to what's going on in the iterated integral as well? I can. First, let's think about what's happening in the inner integral. Well, remember what this represents. Come back over here to our original picture. We're fixing some value of x and then letting y vary and just doing the integration there. Well, if I bring that back over to this three-dimensional picture, that would be like fixing the value of x somewhere, let's just say back here, and letting y vary like that. Now, as I'm going along, I'm always evaluating the function at those points. But if I'm thinking of the function as representing the height of this graph, that means that everywhere I move on that blue line right there, the weight I'm giving to all my infinitesimals will be that height. So the value of that inner integral is going to be, geometrically, the area of this blue figure right there. Looks kind of like a razor blade. So that inner integral gives me the area of that razor blade. But the particular razor blade, whose area it's finding, depends on that fixed value of x. If my value of x was closer to 2, the razor blade I'd get would be shorter. Once I have the area of that razor blade, the outer integral, which I described over here as sweeping out that full rectangle, or sweeping out the rectangle here, it's like taking that blade and just sweeping it out in space, sweeping out that full crystal in space. So we start getting the area, and then we sweep out the volume with it. And that is the idea of double integrals. Get a double integral, turn it into an iterated integral, and crank out the value of that integral. Geometrically, you can think of those as volumes under surfaces, or at least differences of volumes under surfaces, for cases where the surface might dip below the xy plane. Okay, that is all. So until next time, what language did it was Latin. Vale.